Hello and welcome to today's video. In this video, we're going to introduce a very important kind of functions. Those functions are called linear functions or linear mappings. You've probably encountered linear functions at school some time ago, and you'll encounter them in lots and lots of applications, especially in cases where more complicated functions are really necessary to describe real-world behavior, because in those cases, linear functions are often used as simplifications and approximations to actually get results that are out of reach using the real-world functions. And one popular idea here is to use an approximation by a linear function and then refine that approximation step by step until we get a result that is good enough. We'll revisit that theme when we get to the analysis part of this lecture here. But for now, let's talk about linear functions from a linear algebra standpoint. We'll first define what a linear function is, and then we'll see some examples of linear functions in this section here. Now, linear functions are often referred to as linear mappings as well. The term basically means the same thing, mapping and function. The difference that you sometimes encounter is some authors of certain books refer to a function if the codomain is R or a subset of R, the real numbers, and a mapping if the codomain is something else, like some R to the M. So in this course, we'll use the words linear mappings and linear functions to mean the same thing. So let's start with this section. It's called linear mappings. And we'll start with the definition. Now basically, from a linear algebra point of view, a linear mapping is a mapping between two vector spaces that preserves the structural properties of these vector spaces. Meaning, it doesn't really matter whether you do computations in the domain and then map the result, or whether you map the individual parts of your computation and then do the computation in the codomain. That's the whole point of a linear function. And that's basically the definition too. So for the general setting, we'll have two vector spaces, let V and W be vector spaces. And then we need a mapping, of course, a mapping, let's call it capital F, from V to W is called linear. If the following two conditions hold. First, if we apply f to the sum of two vectors, so f of x plus y, then that is the same thing as applying f to the vectors x and y individually, and then summing up the results. And that needs to be true for all x, y in V. And the second property, if we take a vector x and scale that by a scalar, so we take lambda times x for some scalar lambda, and apply f to that scaled version, that's the same thing as first applying f to the vector x and then scaling. And again, that needs to be true for all v in V and all lambda in R. So that's the definition of a linear function. Now to illustrate that, let's see some examples. First, something that you probably know from school. Let's take a function from R to R. So R is of course also a vector space. And let's just take the function f of x equals 2 times x. Then this function is linear, because if we compute f of x plus y, then by definition that's 2 times the argument, so 2 times x plus y. By the rules of computation for real numbers, that's the same thing as 2x plus 2y. And now here, this here is exactly f of x. This here is f of y. So we get this is f of x plus f of y. So that means that first property of linear function holds in this case. And for the second property, let's check f of x plus, f of lambda x. That is 2 times lambda x. Or we can just rearrange that, lambda times 2x. And that in turn is lambda times f of x. So those two properties hold. And that means f is in fact a linear mapping. Okay, let's talk about B, second example. We'll generalize that setting a little. We now have a look at a function that maps R2 to R2. And let's say we have a mapping of the form f of x1, x2 is defined as A times x1, x2 for some matrix A in R2 by 2. Then if we have a look at f of x plus y, by definition that is matrix times x plus y. And by the rules of matrix multiplication, that's the same thing as ax plus ay. So again, we have f of x plus f of y. And of course, the same is true for f of lambda x. That is A times lambda x. And by definition of matrix multiplication, this scalar, this lambda, can be written anywhere. So you can just take out that lambda here. And then you have lambda times ax, which is lambda times f of x. And you will have noticed this works for every possible matrix. So that's not limited to R2 by 2 matrices. So every function defined in that form, f of x equals a matrix times x, every function of that form is a linear function. So for any matrix A in R to the m by n, it doesn't have to be a square matrix. So m by n is fine. The function f that would then map R to the n to R to the m, defined as f of x equals A times x, is linear. So here's a large class of linear functions that are defined as matrix times vector. And of course, what we saw here in example A, this function here, that's a special case of that second idea here, because in this case, the vector spaces involved are both R r to the 1, so one-dimensional spaces. And that means if we want a matrix representation of that, we want a 1-by-1 matrix. And this here, this 2 is exactly the 1-by-1 matrix that we're looking at. Okay, so A is a special case of B, indeed. Let's have a look at a more abstract case as our third example. Let's say we have a function capital F that maps from R4 to P3. And remember P3, that is the space of all polynomials of degree at most 3. And we'll define the function as f of a0, a1, a2, a3. We'll start the counting at 0 for reasons that will become clear in just a second. So that is a vector in R4. And we'll define that function to be a0 plus a1x plus a2x squared plus a3x3. So for example, f of 1, 2, 0, 1 would be the polynomial 1 plus 2x plus x to the third. No x squared, so x squared is associated with a 0 here. So basically that's the mapping that works on the coefficient space, if you want to say that. Space of coefficients, and then maps that to a polynomial. And that is also a linear mapping. And you can see that if you just do the computations here, so that's a little more to write. Still not very complicated, hopefully. So if you have f of a1 of a plus b, so we have f of a0 plus b0, a1 plus b1, a2 plus b2, a3 plus b3. Then, by definition, that is a0 plus b0 plus a1 plus b1x plus a2 plus b2x squared plus a3 plus b3 x to the third. And of course, you can now go ahead and reorder that and rearrange that a little. So let's collect all the A terms and all the B terms separately. Then we have A0 plus A1x plus A2x squared plus A3x to the third. And for the B terms, B0 plus B1x plus B2x squared plus B3x to the third. And that is the same thing as f of a0, a1, a2, a3 plus f of b0, b1, b2, b3. Very simple. And of course, the same idea works if you look at f of lambda a. Now that's the same thing as lambda a0, lambda a1, lambda a2, lambda a3. That is lambda a0 plus lambda a1x plus lambda a2x squared plus lambda a3 x to the third. And of course we can factor out the lambda here, so that's lambda a0 plus a1x plus a2x squared plus a3x to the third. And that in turn is lambda times f of a0, a1, a2, a3. So again, f is a linear mapping. And finally, let's have a look at an example of a mapping that is not linear. We'll again have a look at the very simple case of functions from R to R, and we'll define our f of x as 2x plus 1. And I claim this is not a linear mapping. Why is that not a linear mapping? Well, there's basically two possibilities to prove that. What you can always do, and what you should always do if in doubt, is you provide a counterexample. And of course you can do that here. Let's try the first property here. So if we want to show something like f of x plus y, is that equal to f of x plus f of y? Now let's write down that property. That would mean that 2 times x plus y plus 1 needs to be equal to 2 times x plus 1 plus 2 times y plus 1. Now you can already guess that this is obviously going wrong here. So we have 2x plus 2y here plus 1, and we have 2x plus 2y plus 2 on that side. So for example, if we take x and y to be 0, then we get f of 0 plus 0 is, well, by definition, 2 times 0 plus 1, so that's 1. But f of 0 plus f of 0 is 2 times 0 plus 1 plus 2 times 0 plus 1, and that's 2. So here we have a contradiction, and that means that first property is not fulfilled, obviously. More generally, when you have a linear mapping, we have the following property. We can have a look at f of the 0 vector. Now f of the 0 vector is obviously the same thing as f of 0 times the 0 vector, which is by linearity the same as 0 times f of the 0 vector, or any vector really. And 0 times anything in a vector space is always the 0 vector. So that means a linear mapping always has a property that it maps 0 to 0. So a linear mapping always maps the 0 vector to the 0 vector. And then in the codomain, yeah? So those two 0 vectors might be different vectors. They are both 0 vectors of their respective vector spaces, but of course the vector spaces may be different. So the one vector space may be like r to the 3, and the other may be r to the 5, and then you have the 0 vector 2, 0, 0, 0 in the domain, and in the codomain the 0 vector is 0, 0, 0, 0, 0. So it's not formally the same vector, but a linear mapping always maps the 0 vector of the domain to the 0 vector of the codomain. And that's also something that's not true here, and you can see that easily in that example. So here the 0 vector is just the number 0, and f of 0 is 2 times 0 plus 1. That's 1, and 1 is obviously not the zero vector of the codomain, which would also be 0. So here's a very, very easy criterion to find out whether a given mapping might not be linear. So that's an exclusion criterion. One thing I would check first if I'm giving a mapping and don't know whether it's linear or not, or don't have a good suspicion of whether it's linear or not, I check the zero vector. So if f of 0 is 0, then we still have a chance for the mapping to be linear. It need not be, but it could be. If f of 0 is not 0, then we have completely excluded that. It cannot be linear anymore. Okay, so this completes our introduction, our definition of linear mappings. And in the following videos, we'll investigate some properties of linear mappings. And we'll also go a little deeper into that connection between matrices and linear mappings that we have seen in one of the examples in this video already. And as always, I hope I'll see you then.